and share my screen. There we go. And here we go. Good morning, everybody. Let's get into our hacking moods today. There's a handful of just sort of setup stuff for us to make sure that you have up before we start talking about actual material today. So right now, what I'm looking at, I'm in the topic 05 folder under our GitHub repo. And in this folder, there are two files here that we'll be going over this week. They're located at this notes_files.py and this notes_unicode.py. This is the one that we're going to be starting with today. Maybe we'll get to this one today. Maybe it'll be a Wednesday thing. Again, if you want to download one of these files to follow along, you always click on the file. And then you don't copy and paste. Instead, you right-click on the raw button over here. Right-click there. Assuming your mouse is working, right click there. Or you can just click there and my right click doesn't want to stay up for some reason. But then you can go file. Oh, I guess none of those things want to work, but somehow actually saving this to your computer, easiest way to do it is right click on the raw, go down to save as. And that'll download this file, which is the thing that we will start with today. Other good things to have up that we'll be referencing are your strings quiz practice. This, again, is going to be the quiz that we'll be having this coming Wednesday, next class period. So far, we have talked about most of the stuff on this quiz practice up until the very, very last few problems. Like we've gone up to problem 20, have not talked about what's on problem 21, and we're going to figuring out what's going on here in problem 21 and 22 will take us most of today. It'll be a big detour around things that don't look like what we were talking about before, and then we'll finally get back to this quiz material, these last two problems here, and you'll see exactly what's going on with these problems. So it's a good thing to have out, so a good place to take notes, again, so that you have access to the material on the quiz, because you can use any handwritten notes that you want, but not electronic things. Also, the Ascii cheat sheet, the Ascii chart right here, is something that we'll be referencing as well. Any questions on just the setup, what files we're going to be going over today? Repeat everything? The files that under this folder that we'll be using today, this notes_unicode is the main one. We probably won't get to this files one. That'll be for Wednesday. But yeah, this notes_unicode, that's the main thing to have to follow along. When you get it opened up in VS Code, it'll look something like this. There'll be a bunch of foreign language stuff, and that's how you'll know that things are opened up correctly. Question?
Super small note. It's interesting. Under the Arabic sign, it says U+200F. Around
so we'll go over all that weird stuff here in a little bit. There's a lot of weird stuff with foreign languages in programming. So yeah, before we get into the actual code, while you all are bringing that up, I just want to do a highlight overview, big picture of what we'll be talking about today. And this is all contained in the readme.md file. So today we're talking about this thing called Unicode. And Unicode, question before, yes. I don't have any spare physical copies. In order to get electronic copies that you can print yourself of any of these documents, back in the, so this is the main repository, the main location of the repository for our class. Anytime I pass something out, the PDF file for whatever I passed out will be in the week that I passed it out in. So last week is when I passed out the information for this quiz, and this file right here, this quizpractice.pdf, is the file that will be relevant for as the practice for this week's quiz. Okay, so yes, Unicode is this international standard for representing text. I wrote here for representing text as numbers, but really it's for representing text on the computer. And it's for working with any possible language. One of the key benefits of Unicode is that any language that has ever existed or ever will exist, Unicode's mission is to make it representable on computers. And so we saw previously that with this Ascii chart, every number, every letter on a computer somehow is represented by a number. So like the letter capital A right here is represented by this number 65. And Ascii was one of these first sort of representations, these first systems for representing numbers as letters and vice versa. And it only supported English at the time. So it was invented in the 1960s. At the time, computing resources very limited, and people in the US only needed support for English, and so this is what they started off with. Their Unicode is not something that is covered in the textbook at all. So this is the reference. If you want a written reference of all the things that we'll be talking about today, this is what to look at right here. And again, it's totally freely accessible material. You don't have to pay for it at all. And not only is Unicode something that's not in the textbook, it's actually not commonly taught at all to computer science majors anywhere in the United States. So for example, I've talked to the professors at MUD and Pomona. I've talked to people at MIT, Stanford, went to the Naval Academy and Johns Hopkins and UC Riverside. None of those schools teach Unicode to their computer science majors. And to be a little bit sort of facetious about it, it's because Americans think that everybody should just learn to speak a proper language like English. And we don't really care about supporting these other languages. And this is one of the things that companies really complain about a lot when they're hiring new grads into programming positions or into project management sort of positions, is that if you're at Facebook or Microsoft or any of these multinational companies that actually have to work in the real world, you actually have to work with people who don't speak English. You have to write code that works for their use cases. And so they really wish people knew about Unicode, but they don't know about Unicode. So that's why we're including it in this course here. It's also particularly important for data science applications, because if you want to somehow analyze the text that people are writing, you have to be able to understand how that text is actually represented. Okay, that's my preamble, and let's switch over to the notes unicode.py and talk about how this all actually works. Maybe one more preamble before we get into the technical meat of things today is that for most students who have not previously had any sort of programming experience, the last 2 to 3 weeks of this course are extremely difficult, even for people who have programming experience. There's just a lot of material in these last few weeks, and it's all very technical. And so I intentionally put this here in our sort of 4th week of Python, because most students find this relatively easy compared to everything that we've talked about so far. That said, students who have had some prior programming experience, I guarantee you have not seen any of the stuff that we will talk about today. And so if you sort of zone out today, then you're not gonna know how to do any of this stuff, which will be important. Okay, so in Python, one of the reasons that Python first became a famous popular programming language is that most things related to foreign languages sort of just work in Python somehow. And so here you can see that I have a couple of different variable names over here in different languages, and the contents, the value of each of those variables is computer programming is the best, just translated into all these different languages. And Python, we'll see here in a second, is able to just do basically what you would expect for all of these different things. I'm going to, down here in the bottom, open up interactive Python in a slightly new way that we haven't seen before, in order to be able to access these variables from within this file. Up here in the top right, I'm going to press this triangle button. Again, the triangle button just copies and pastes some code down here into the terminal. It's always composed of two parts, whatever looks like Python 3 for your particular computer, however to run Python, and then the name of the file that you have loaded up here. In order to be able to get interactive Python, we've seen before, one way of doing that is just deleting all of this file name like this and running Python 3 by itself like this. Whatever that command looks like for you, you hit enter and you know you're in interactive Python because it has the 3 greater than signs down here. And you can type in Python code like 1 + 2 and it runs that Python code. But if you run interactive Python this way, you're not able to get access to any of this information, any of these variables that are defined in the Python file. So like I have this English language variable, English like that, I hit enter, and we get this error saying that English is not defined. In order to have access to this information, so again, I can leave interactive Python with this exit command. It goes back to the ordinary terminal. I know it's the ordinary terminal for me because it ends in the $sign, but for you, it'll look different. The important thing is that it's just not this triple greater than sign. In order to get interactive Python with access to all of these variables, I will do the triangle button again, press the up arrow, and then in between the Python 3 and the file name right here, I add the -i command like this. So this is the same spot where we used to add the -m doc test, but now we're adding -i, the I standing for interactive. And what this is going to tell Python to do is to go into interactive Python mode. Again, I know I'm in interactive Python because I have the 3 greater than signs right here. But now if I type something like English, I'll have access to this variable up here. Or if I type something like Chinese, then it's going to give me that variable right here with this contents matching this contents defined in the file up here. Henry.
So this isn't specific to foreign languages. This is just specific to anything you define in the file, you can access it, use the -i.
Yeah, this is a great question. The question is this -i somehow specific to the content of today of like Unicode or foreign languages? And the answer is no. Anytime you're working with a Python file in VS Code, you can always do this to get into the interactive mode. It's just that this interactive mode is going to be particularly useful today as we're working with these foreign languages. Good question. Any other questions so far? Jackson.
It says I have an error. It says trace back.
If you have an error, if you're getting an error from running this command, it means that somehow your Python file right here is corrupted or not correct. And you should try re-downloading it from GitHub, making sure not to copy and paste, especially with foreign language things. Copying and pasting very likely to screw things up.
Isn't it also case sensitive, like Chinese is case sensitive?
Yeah, so we've talked about Python previously is case sensitive. So like this English language variable with a capital E is different than English with a lowercase e like this. Exactly what it means to be case sensitive is different in different languages, and we'll talk about that here in a second. But traditionally in Chinese characters, there is no like uppercase or lowercase of a Chinese character. Okay, so let's see. So we've seen before that if we do indexing on a string, so here's the English string, indexing works just like lists. And so here is the 0 character right here of this string. And so if I do English at position 0, I get C. Similarly, things work very similarly for other languages. If I do Chinese at position 0, that gives me this character right here because it's the very first thing in the string. And then if we do something like Korean at position 0, it also gives me the very first character that's being displayed up here. For the most part, things at this point are just going to work. Depending on the fonts that you have on your computer, your display might not look exactly like this, but you might have some extra characters, extra weird things being displayed if you don't have the right fonts installed, which would totally make sense if you're not like using Korean all the time, that you wouldn't have the Korean fonts installed. Most of these languages are written left to right. And so English, Chinese, Korean, Vietnamese, all written left to right. Arabic is different. It's traditionally written right to left. And right now, if I click on the Arabic, I'm pressing the left arrow on my keyboard. Now I'm pressing the right arrow. And you can see that the text is actually moving backwards. You can't see what I'm pressing, but you can believe me that I'm pressing the left key right now and it's moving to the right instead of to the left. And then when I hit a space, you can see that the cursor sort of jumps all over the place because the space is represented using normal English. So the space is written left to right, but everything else is written right to left. And it's perfectly okay in Python to combine multiple languages together, a very common thing to do, and no problems with that at all. It's possible, although extremely rare, basically nobody does this, but it's possible to use whatever foreign letters, non-English letters that you want inside of variable names like this. So this is computer in Korean right here. And it's fine to do that. Nobody does that because yeah, a Korean keyboard would have these letters. It's easy for somebody to type, but if you want to share your code internationally, that becomes very difficult for non-Koreans to work with. And so it's traditional, no matter where you are in the world, to only use English letters for your variable names. And finally, emojis basically just work as well. Any weird character that you might want to think of just works, assuming that you have the font installed. If you don't have the font installed, then depending on the exact character, you might get something different displayed, but the square box like this is the traditional thing that gets displayed to indicate that you don't have that character available. Right here, you can see that these two things look like they're the same thing, but if I type emoji 3, so I get a box in there, emoji 4, and emoji 3 equals emoji 4, the double equal sign, again, doing the comparison, and we'll get false, even though it looks like it's being displayed as the same thing. It's just because I don't have those characters installed. And so they're both being represented as boxes, but they're different things, so they're not equal to each other. 99% of the time, that's all you need to know, is that things just work unless you have the font not installed. Everything else that we're going to talk about today is that like weird edge case 1% of the time stuff. So before we get into those weird edge case stuff, any questions so far? Okay. So the first thing is that some things are just weird and there's like nothing we can do about that. So for historical reasons, some characters also contain font information inside of them. So this is all inside of italic right here. And this text right here, like the content of this text, the meaning of this text is the same as this one right here, written in this fractor font. But if I type italic down here and fractor down here, you can see that they're both being displayed. But if I do italic equals fractor like this, you'll see that I get false. Because even though like the letters and the words are somehow the same, because the font is different, then it's not getting compared correctly. It's not doing the comparison. And there's a lot of these weird different fonts somehow built into Unicode. This typewriter font called the teletype, some upside down things, putting things in circles. And there's only a very small number of them. But that's one of the weird things that there's just nothing you can do about. Another thing that's sort of linguistically just weird is that normally we think about, so here if I type German like this, normally when we convert something to uppercase and convert something to lowercase, it doesn't change the length of our strings. But here in German, if I do German dot upper like this, you can see that this character right here got changed to the double S like this. This character, depending on like which German dialect you're from, has a bunch of different names. But the ersatz is one of them. And the lowercase version of the ersatz character is just a single character, but the uppercase version is 2 characters like this. And so for German text, if you convert something to uppercase and then convert it back to lowercase, you're not guaranteed to get the same thing back. because that ersatz character will be converted into 2 S's like that. And that's just a weird thing about the German language that computers have to deal with. And as you're writing code, you have to be aware of that converting things to uppercase and lowercase. In English, in most languages, that doesn't change the length of a string, but it could change the length of a string in some languages. Another weird thing is that numbers in many languages don't behave the way that you might expect them to. So in Python, if I have something like the number 89 like this, we know that this number right here is actually a string and not a number because it has quotation marks around it. We can always use this type function to actually tell you exactly what the type of something is. So it tells me that this is a string right here. If I were to take away those quotation marks, it would tell me that it's an integer like this. And there's this function int, which will convert a string into an integer. I know it's converted a string into an integer here because down here there are no quotation marks around it. So this int function will convert a string that contains a number into the number itself. If I type in numbers down here, so here is this number that looks like it's the number 89, but now if I convert that into an actual integer, into an actual number, this number that looks like the number 89 is actually the number 47. It turns out that in Tamil, the Tamil language, this 8-looking thing is how they write the number 4. That equals 4. And this 9-looking thing is how they write the number 7. And so when you're working with numbers that are stored as strings, you just have to know that, like, just because you're looking at it and it looks like an 89 doesn't mean it's actually an 89. Whatever Python says it actually is what it actually is to the people who speak that language. Another problem is that some characters in some languages look like each other. And we'll see that this is going to lead to a security issue. So here I have 3 URLs. If you've taken your, I don't know, like phishing training that the IT people make us take all the time, and you're going to your bank, you'll always make sure that you're visiting the HTTPS, that it's a secure link, and you look at the URL over here to make sure that it is in fact the URL that you're wanting to visit. But it turns out that these 3 URLs right here are not equal to each other. So URL1 equals URL2 is false, URL2 equals URL3 is false, URL1 equals URL3 also false. The reason for that is that in some of these URLs, like this one right here, this A is not actually the letter A. It is the uppercase Greek alpha character. Oops. So this one over here is the actual Bank of America website. This one down here is the Bank of Greek letter Alpha America website. And because the font that I have installed happens to display the uppercase alpha the same as the uppercase A, they look the same, but they're not actually the same. Down here, if I type Greek like this, so here's the letters of the Greek alphabet. Greek at position 0, give me that alpha dot upper, convert it to uppercase like this. So this is the uppercase Greek letter alpha, not the English letter A. Set that equal to the letter A like that, you'll get false. These sort of tricks, security sort of issues are a major source of like hacking techniques that if you can convince somebody to click on a link that looks like this, then like I would be fooled into thinking that I'm at the Bank of America website. There's really no realistic way of not knowing, of just looking at this and knowing that it's not bankofamerica.com. Switch over here, there's a couple of fun links down here. One of those fun links is the National Security Agency has a big PDF file. It's like 100 pages or so of different ways that you can use Unicode to try to hack into people's computers doing something like this, or to trick people into clicking on bad links. Question?
I think all of our Python that make with little yellow boxes around it show us what's there and what's not there. It's like character, the or A is visible, or is it plus is going to show us what's there? It's not.
Yeah, so depending on how your system is set up, especially if you don't use multiple different languages on your computer. Let's see, if I go and put this into a web browser, for example, let's come over here to Firefox. Because I do not regularly visit Greek websites, you can see that the Greek letters up here got converted. It's a little bit small, I can't zoom that in. But you can see that the Greek letters got converted into non-Greek letters for me. Because I don't regularly visit Greek websites, my Firefox is set up to do that. But people who are Greek speaking will want to have Greek websites show up with the normal Greek letters, and so their Firefox will be set to display those Greek letters. A lot of these language things are going to be very, very like specific to how your computer is set up, and it'll be different on Mac versus Windows versus whatever you happen to be using. Yeah, good question. That yours may or may not actually display exactly the same as mine. Any other questions so far? Okay, so last thing is that some characters in Unicode don't have any display value. They have various control properties that change the way the text looks. And so here, this contains a bunch of actual empty characters with no display. I type empty down here. You can see that Python actually shows those characters down here. And if I type length of empty, then there's 42 of these weird displayless characters. And depending on how your VS Code is set up again, this may or may not look something like this right here, or it may display as empty. No matter what though, if you come down here and do something like print empty, it will always be displayed as actually printing like actual empty down here. And if you print URL1, assuming you have the right fonts installed, once things are printed, it always displays these same values. So printing, just like printing converts the \n into an actual new line right here. We call it the \n. Test1, test2 puts a new line right here. Printing will actually like make things visible, even if Python by itself or VS Code by itself doesn't make those weird characters visible. Main takeaway from this is just to give you some sense about some of the weird things that go on with foreign languages and computers, things that you maybe have not thought about before. There's about 10,000 or so languages that are actively spoken today. Many more if you go into like what Unicode actually supports due to like historical use, or Unicode supports things like Klingon and Elvish as well. And so all of those languages just have weird edge cases that things that you would never even think about. And that's the main takeaway, that strings in Python are weird, and they're weird in ways that you probably won't expect. Any questions about any of that so far? Okay. So then now let's get into some of the technical bits of how we deal with this weirdness and like what you actually need to know while you're programming Python. So the first thing is that, again, Unicode is this standard system for representing all languages on computers. And Python 3.0 was the first major language to have good Unicode support somehow. Exactly what we mean by good here is like, I don't know, maybe up for debate. Some people like what Python 3 does, some people don't like it. But everybody agrees that Python 3 was very like pivotal in paving the way for Unicode support, and that it's one of the reasons it became such a popular programming language. Languages like you may have heard of or used, C++, Java, it's possible to use Unicode have Unicode support, but it's not trivial like it is in Python. Okay, so about Unicode, some key definition words that we'll go over today. The first one is graphene. And again, these definitions, these keywords are not things that I'm ever going to ask you to define. They're just things that you're going to see in context, and we'll have to know from context what we're talking about. So grapheme is what Unicode calls an individual unit of text that is being displayed. And most people would informally call it like a letter or a symbol or a character. So everything that you can see that's like one discrete thing is a grapheme in Unicode. And then a font is the actual pictures that are associated with each grapheme, what actually gets displayed. So down here, this accents_1 and accents_2, these are both the same grapheme. Down here, both the same grapheme because they're both the same thing, like physically being displayed. And both of these are just a single grapheme. Graphemes, though, can be composed of one or more characters, and characters in Unicode are much less intuitive than graphemes. Down here, I'm going to type, so accents_1, we'll see there it is, accents_2, there it is. These two are the same graphemes, but if I do accents_1 equals accents_2, oops, spelling things correctly like this, we'll get false. Because even though these are the same graphemes, they're not actually represented the same way inside of Python. And this first note, this first key thing to be aware of is that equality in Python and actually all programming language is not based on this idea of grapheme equivalence. These are the same graphemes, but they're not the same strings. And instead it's based on character equivalence. So we need to see like what exactly is a character. And the first thing, another note, is that this length function will tell us the number of characters in the string that we have. And so if I do length of accents_1 like this, we'll see there's only one character representing one grapheme. But under accents2, there's actually two characters right here that represent this grapheme. The idea is that in this accents_2, we have a character for A and a character for the accent mark. In order to see how that works, every Unicode character has a code point associated with it, and that code point is like the number. So if we come back over to the Ascii chart over here, this rightmost column over here is the character, like the thing that's like the semantic meaning of each one of these numbers, and the number over here is the code point. So the capital letter A has code point 65. And all of these things turn out to be equivalent representations of the accents_1 right here. This right here is equivalent representations of the accents_2, where we have this A, and then there's this special thing over to the right of it that is going to somehow modify the A to add an accent mark. Anytime, again, you see a backslash inside of a string, the backslash indicates that this is somehow a special thing. So again, we've seen that if we have print test \n test like that, the \n is somehow special because it gets converted into this new line character. All of these things up here are special things representing the A with the accent mark. So these backslash, whatever it is, represent the A with the accent. And then down here, these backslash, whatever it is, represent add an accent to the previous character. So these things, this way down here of writing out strings is a little bit more versatile because I could add an accent mark to whatever character I might possibly want. So again, if we have accents1 like this, it's being displayed as the A. This is, so there's one. When A also like this. When B also like that. C. 2, these all look the same. But now if I do copy and paste this right here and change this to like an E, I can get an E with an accent mark. Or if I don't think there's any languages that actually have a B with an accent mark. So there's no, it's not actually drawing one that you can easily see right there. There we go. Here's a C with an accent mark. This character doesn't have an individual code point like this, an individual one of these things that you can use, but you can still construct that character if you really, really need to for some reason. We're going to see exactly how to create all of these things in detail here in a little bit, but at this point, it's okay just to think about these things are magic. If you see like a backslash and then a bunch of characters, then it's just like magic that you don't need to know, you don't need to understand exactly how it's working. Any questions so far? Okay. So then let's go into this, like exactly how these things are working then. If we come back over to our Ascii conversion chart over here, and I want to write this letter A with this special notation, then what I can do is \x, and then again, the X stands for hexadecimal. Come back over here, find the hexadecimal corresponding to A, this 41 right here, and do so \x 41 like that, and that gives me this uppercase letter A. If I want the lowercase letter a, then find the lowercase letter a in this ASCII table, find the hex is 61, come back over here, change that 41 to a 61, and that gives me this lowercase letter a like this. All these numbers that I have right here, so if we look at this E1 right here, \x E1, we'll see that that E1 is not in this range of ASCII at all. ASCII ends at 7F. E1 is bigger than 7F. And that's because the ASCII doesn't have support for the A with the accent mark. The number E1, if we want to know like what is the actual number associated with E1, I can do 0x E1. Again, this is how you write hexadecimal numbers in Python, and it will convert it into decimal numbers for me. So this is the decimal number corresponding to the E1 number. This number right here is too big for the ASCII conversion chart, so I'm going to try with the \x 41 again. 41 gets associated with 65 in decimal. 0x41 is the hexadecimal number, 65 is the decimal number. And coming back over here to the ASCII chart, 0x41 is the hexadecimal number right here. 0x41 corresponds to 65 in decimal. 65 in decimal, 41 in hex. And I know that because when I type 0x41, it gives me back 65 in decimal. If I need to type only one of these numbers that has a range up to 255, I can use this \x notation. But there's a lot more than 255 different letters in all the languages that exist. And so this lowercase u and this uppercase u notation give me more ranges to type in larger numbers corresponding to fancier or weirder or less English sort of languages. In this case, E1 still, you just add zeros in front of it to use the \lowercase u. To use the uppercase u, you add a lot of zeros in front of it. The lowercase u always has 4 characters after it. The uppercase u always has 8 characters after it. And that's what allows it to represent the larger numbers like this. All of these are entirely equivalent to each other. If I type accents_1a equals accents_1b like this, we'll get true. Even though up here I did not type these, I did not define these variables the same way. These things are equivalent to each other in Python, that they'll get stored with the same underlying representation of just a single character that has the code point of E1. And that's true for C as well. And it's also true for the one which was typed in without this special representation, just typed in directly like this. Similarly, for this other way of representing things, breaking up these letters into two separate pieces, this A and then the accent mark over here, you can see I can't use the \x form to store the accent mark because it has 3 significant digits, this 301. If I type in \x0301 like this, we get the number 769. The code point 769 represents the accent mark right here. 769 is bigger than 255, so I can't use this notation, but I can use these two notations, the lowercase u and the uppercase u, to represent that. And if I do the accents underscore 2b equals accents underscore 2c, that is true, underscore 2, that is true, but comparing to any of the 1 versions, it's going to be false. So no matter how you enter a string into Python, using whichever one of these notations you prefer, it doesn't actually change the value of the string at all. Any questions on that so far? Yes, Jackson.
How do we know 301? It's not on the, is it on the table here? We just kind of look it up.
Yeah, so the question is, how would you know that this 301 happens to correspond to the accent marks? And the answer is that, yeah, you'd have to look it up somewhere. I think what I actually did on mine is I switched my keyboard into Spanish mode and typed in an accent mark, and that's what it gave me. But yeah, just like Google what is the Unicode code point for whatever you're trying to do, it'll come up with the right number. There's, again, at this point, millions of these code points to find. And so nobody has like a printed out cheat sheet of the Unicode code points. Although everybody, vast majority of programmers would at some point in their life have used one of these Ascii cheat sheets. So that sort of segues us into, like, for the quiz, what do you need to know for the quiz? And for the quiz, I'm not going to ask you anything that's not on the Ascii cheat sheet. So for the quiz on Wednesday, you'll need to be able to convert between the Ascii code points into the Ascii value, but you don't need to know like these larger Unicode code points that are outside of this Ascii range. And so, for example, if we come over to this quiz practice down here on problem 21, then we have these letters down here. I'll type that into Python \x. Somebody, so 48, 45, 4C, 4C, 4F. 48 \x, 45 \x, 4C \x. 4, what's that? Somebody shout it out. 4F. There's 2 4C's \x, 4C \x, 4F, like that. And that gives us the value of hello, like this. I know it's hello because, or the way you would on the quiz know that it's hello is this \x48 right here. This 48 is a hexadecimal number 48. So I have to come over to my Ascii cheat sheet, find the hexadecimal 48, which is located right here. The hexadecimal column is over here, 48, and that corresponds to the letter H. So the \x48 is entirely equivalent to the letter H like this. No difference at all between those two things. Subtle thing for the quiz is this problem 22 right here. It's so up here on problem 21, I only included these this sort of like ASCII \x way of entering things. Down here on problem 22, it's a mixture of the \x technique and other techniques, or the standard techniques. So there's 57, 72, 44. So it's \x, 57, \x, 57, 72, 44, 57, 72, \x, 44, like this. I hit enter, and we get a world like this, mixture of lowercase and uppercase. This right here is the W. This O looking thing is just this O right here. It's easy to overlook this O thinking that it's part of one of these like \x commands, but \x always looks at exactly the next two locations, and this is after the next location, so it's just a regular O. Then there's this \x72. This L right here, just a regular L, corresponds to this L, and then \x44 corresponding to that D right there. So you have to be pretty careful when you're working through something like that on the quiz, making sure that the individual letters, you don't mix those in your mind with the escape code \x letters. Guaranteed to be at least one of these problems on the quiz. So make sure to ask questions about it if you have them. Yes. The \x is how you insert, is how you reference any character by its code point, whether it's ASCII or non-ASCII. So on the quiz, I'm only going to ask ASCII values because you will have your ASCII cheat sheet available to look up exactly what is the appropriate letter for each of these hexadecimal values. But something like this \E1, that's not an ASCII value. It's too big to fit in ASCII, but it's still something that you can use the \x for. Did that answer your question? Okay. Yes.
So if it's \x57O, even if it was like O, Q, R, none of those would print, or none of those would like be registered to the order of the next.
So something like this is going to give you this syntax error right here, because whatever comes after the \x must be a valid hexadecimal value. Q and R are too big letters to be hexadecimal. So something like this cannot work. You will not have something like this on the quiz. You would have to, the biggest letters you can have after it are F, something like that would. Reads the next two after that.
But you said how O wasn't, like the 57O, the O doesn't do anything?
Well, so it's not that the O doesn't do anything, it's that \x57O, it's that this is the first character right here, this is position 0, this is position 1 right here. The O doesn't affect the backslash.
Okay.
Do that, it's the WO. The W corresponds to that. For code point 57, the O corresponds to the O right there. Jackson?
I have 2 quick questions. One, what if it was X57 and then like, I don't know, it's got to be 70, like 5770. Okay.
So \x always looks at exactly the next two things and nothing beyond that. If this was \u, then it would look at exactly the next 4 things. This happens to correspond to that Chinese character.
And then I guess the other one is for problem 20. I typed it into my computer. It was print 0x0010. How do we know that's 16?
So the question is, on the previous problems, 19 and 20, if you recall that there are on, normally when you're entering numbers into Python, you're entering them in decimal, but if you put a 0x in front of it, that 0x, that X right here stands for hexadecimal. And so that gives me 16 because 10 hexadecimal is 16 decimal. I know that using my ASCII chart up here, looking up the Python conversion, find 10 hexadecimal, hexadecimal 10 right here corresponds to 16 decimal. So I may ask you to convert between hexadecimal and decimal values, and you have to know this syntax for doing that, but the range is only going to be the numbers that somehow fit inside this ASCII table. You don't actually have to do the computation yourself, you just have to be able to know how to look up which hex or octal or binary value corresponds to which decimal value.
So how come there are extra zeros in front, but that doesn't have any impact?
Question is, how come there's extra zeros in front that doesn't have any impact? Just like if you add extra zeros in front of a decimal number, it doesn't affect that. Right.
Where can we find the quiz questions?
Question is where to find the quiz questions, and You can always find the material that I pass out on the week that I passed it out in. So I passed it out last week, so it's under the topic 4_quiz practice.pdf. Same question? Okay, related to all of this, there's two functions, ord and char, that help us figure out what the code point of an individual character is, or what the character is for an individual code point. The ord function goes from string to integer. The char function goes from integer to string. If I have something like, so \x_e1 like this is an individual character. If I use the ord function on that individual character, it'll give me the number corresponding to that individual character in decimal. And that is the same as if I were to manually do that like this. So converting this number over here from hexadecimal, type it in hexadecimal as an integer instead of as a character. And Python, when it displays it, it's going to display it as a decimal integer in both cases. So ord gives me the code point number of a character, and then the chr gives me the corresponding character back if I want it. So this is somewhat useful to like maybe iterate over all the different types of characters. Here's an A wearing a hat, an A with a squiggle on the top. And you can just get a sense for what Unicode has to offer by playing around with different sort of values like that. Okay. All great questions so far. Again, this is what you need to know for the quiz this coming Wednesday. So any other questions about these different representations right here? Is that a question?
Yeah. Why is it that you just put the straight number values into the asterisk on either side?
You're referring to these things up here, or were you down here?
Yeah. Why is it that you just?
Why is this just a number?
Yeah, rather than.
So the char function just takes a number as input. If I were to put strings around it, then it gives me this error method. So char and ord are for converting between numbers and strings to find the code point that corresponds with a particular number. Okay, so what we'll see from this point on is things that you'll need for the lab this week, but again, not for the quiz. And this is like this idea. Okay, again, what we saw, this first weird thing is that accents 1, accents 2, the graphemes are the same. So we should really want that accents 1 is equal to accents 2, but depending on how the person happened to input it into the computer, it might be represented in different ways. And so comparing things could get me false, even when things look exactly 100% the same. So how do I make it so that these two things are actually represented the same? And that's called character normalization in Unicode. Character normalization means taking the graphemes and representing them in some sort of standard way. There's 4 standard ways. The first 2 and the most important 2 are NFC and NFD. NFC standing for composed, normal form composed, NFD for normal form decomposed. And you have access in Python to tools that will do this for you automatically with this Unicode data library. It's built into Python, not something that you have to install at all. And here, if we have, so this function right here, Unicode data.normalize, takes whatever string you have and puts it into this particular form, whatever form you type right here. So this normalize function takes 2 arguments. The one on the left is the form that you're converting to. The one on the right is the string that you're converting. And we've seen before that accents 1 is not in fact equal to accents 2. But if we convert them both into the same normal form, in this case NFC, and I do accents_1_NFC equals accents_2_NFC. If I convert both of these 2 things into the same normal form, then they will in fact be equal to each other. Now it's true. So comparing these two things directly is false. Converting them both into this NFC form and then comparing them is true. Converting them into the NFC form means that I'm somehow going to be comparing them semantically on their graphemes instead of on their underlying representation. What NFC form means is, so if I do the length of accents underscore 1 underscore NFC, we get that it's the length in both cases is 1. The composed normal form means that if possible, represent all the characters with a single code point. So instead of storing two separate code points like the A and the accent mark separately, store it as a single A accent mark, and it'll convert that into something with length 1. The length of accents 2 is 2, but when I normalize it with the NFC form, it's going to give me length 1, like this. Similarly, if I do the D form, it's going to go the opposite way, breaking things out into as many parts as possible. Vietnamese is a classic example for this because Vietnamese just has accent marks everywhere, all over the place. So like this A has 2 accent marks on it, one above, one below. It's got the hat above, the dot below, and various letters with accents going every direction. Here, if I do like this Vietnamese NFD equals Vietnamese underscore NFC, we'll see that that's not equal to each other. The graphemes up here all look the same. So they should be equal to each other, but they're not equal to each other. If I look at the length of the Vietnamese NFD, it's 44. Of NFC, it's 34. All these accents are stored separately up here. All of them are stored the same down here, combined with the letters. And so if I want to do these comparisons with each other, actually compare semantically whether these two strings are the same or not, I have to convert them, Unicode data.normalize, into some normal form like NFC. Vietnamese underscore NFD equals Unicode data.normalize NFC Vietnamese underscore NFD, like that. Oops. Up here, we tried to see if NFD equals NFC. They're not equal to each other. We know they're not equal to each other just looking at their lengths, totally different lengths, so they can't be the same. But if I normalize them both with the same normal form, in this case, I'm going to NFC, then it will actually compare on the sort of semantic meaning level on the grapheme level. So if you ever have strings that you want to compare with each other, then you have to normalize them in order for that comparison to make sense. Doesn't matter how you normalize them, whether you go to NFC or NFD, but you have to normalize them for that comparison to be like the actual semantic comparison. Yes?
If something's already in NFC form and like for example, Vietnamese NFC, would you have to normalize that for it to be equal to NFD?
Good question. So this normalization right here, converting Vietnamese NFC is not strictly necessary. If you already know that your string is in a certain form, normalizing it to that form just does nothing at all. Yes?
Why would you ever use the NFD, especially if it takes up more space and makes them longer and bigger? It's also what you want, right?
Yeah, good question. The question is, like, when would you use the NFD over the NFC? Vast majority of companies and applications use NFC internally. Every time you type in something into Facebook, they always immediately pass it to this Unicode normalize NFC function, converting things into NFC form. And internally, Facebook does everything inside of NFC form. The question is, when would you want to use this NFD form? There's certain like data processing things you might want to do, like you might want to strip out all accent marks from text. You might want to compare, like, you might want to say something like that should be equal to that. And in order to like actually process this, stripping out the accent marks so that those two things are the same, you'd convert it to NFD form, then keep only the ASCII characters. So usually this is only used for like intermediate processing steps, and this is what people actually store things in all the time. Good question. So it turns out besides these two normal forms, there are two other normal forms, NFKD and NFKC. Here the K stands for compatibility because they didn't want to have two C's inside of here. Like they already used C for composed, so they decided to use K for compatibility. And in German, compatibility starts with K. But so here, as an example, I have 4 of these variables with this fractor sort of font thing going on. We saw before that if you have these weird fonts inside of your strings, you can't just compare them directly. They won't be equal to each other. If you normalize, this one should be NFC, this one should be NFD, this should be NFKC, and this one should be NFKD. If you normalize according to the NFC or NFD, these will keep their weird fonts. If you do not have the K in your normalization, it will keep the weird fonts. If you put the K in the normalization, it will take out the weird fonts. So I'm going to save my file up here. Anytime I make modifications to a file when I'm in the interactive Python down here, I'll have to reload Python. So down here, I'll type exit down here, up arrow, get back to my interactive Python command back here like this. And now if I type fractor underscore NFC, you can see that it is still with this fractor font. But if I did NFKC like this, then you can see now it's back to like a normal font. And so something will do something a little bit complicated, remind us of our split function. The split function will split on spaces. And so this gives me the very first word over here, fractor nfkc.split at position 0 equals computer. The answer is true. But if I take out this K, we'll get false because it'll give me computer in this weird font like this. So for most applications, you also want to normalize getting rid of all this like weird sort of font information. Facebook, major companies like that, they want their posts to be able to display with these weird fonts. So they would normalize with NFC instead of NFKC. But if you're doing like data analysis stuff, you want this weird computer word to look the same as the normal computer word, then you normalize with NFKC. Any questions about that? Okay, all of these examples with fonts, weird fonts that we've seen have been just English things so far. Arabic happens to have a lot of fonts with particular religious significance inside of it. So this is one letter right here, a single PBUH like this, a single character length of PBUH. That is an entire sentence in Arabic, the English translation being peace be upon him. If we convert that using this Unicode data.normalize of NFKD like this, so decompose it and undo the weird fonts of PBUH like this, then this is the entire sentence that is being represented as just a single letter up here. And if we take the length of that, that's 18 actual characters that are represented by a single character up here. The basmala like that. NFKD. No, that one's not. That one, for some reason, is staying as one giant thing, which I don't remember why that's the case. But there's like 40 letters or so in that one. That's the longest character in Unicode is the basmala right here. So again, these sort of like weird issues, not just unique to English or the text processing that you might expect, but all languages have these sort of compatibility forms, these things that should be equal to each other semantically, but are not for various reasons. And so doing this NFKC is probably usually what you want to do to do string comparisons. And that's what this first principle one right here says, is that whenever you're comparing strings inside of Python, Python will not normalize this text for you automatically. And so you must choose some form to normalize them in. And NFC is sort of the traditional one, or NFKC if you want to also get rid of this special formatting. But you must always normalize your strings before comparing them in Python. Any questions about that? Okay, more weird stuff then. Sorting. So recall that when we're sorting things in Python, it's done ASCII-betically for English text. And so the capital letters like capital Z comes before lowercase a because we sort on these numbers over here. Well, when we're sorting other languages as well, we sort of Unicode-betically, sorting by the code point numbers. So here, like in German, this A character right here should come before like B and K. But if we type words like that and then words dot sort words, this is the sorted order that Python gives us. And these things are coming at the end because they have higher Unicode code point values. Turns out sorting is a very political topic, and different countries that use the same alphabet use different orders of their alphabet. So like South Korea and North Korea, for example, have different orders of their Korean letters. And so this is at the top is the South Korean ordering. At the bottom is the North Korean ordering. And for various reasons, North Korea was not on the council deciding how things should be sorted. And so the South Korean ordering is how Korean things get ordered, not according to the North Korean ordering. So this other principle too is that it's impossible to actually sort your text correctly in any programming language unless you know some sort of extra meta information about the locale, like where the person is actually located. And in this class, we're not going to talk about using this locale information because it gets a little bit complicated, but in the follow-on class to this, CS46, that's something that you would deal with. Encoding down here, this is the next like main thing that you'll need to understand for the labs and programming parts of this class, but this won't be on any sort of quiz. So how are strings physically stored on the computer? So some quick background. A bit in computer science is either a 0 or a 1. Everything on computers is stored as bits, and we sort of chunk those bits together in bytes in units of 8 bits at a time. 8 bits is convenient because it's large enough to store ASCII values. And so back in the 60s, when people were deciding like what's the most fundamental like size of something on a computer, they decided on 8 bits because that it was big enough to store ASCII values. So a document with 1,000 English characters needs 1,000 of those different ASCII values. Each byte stores 1 ASCII value, so that's a 1 kilobyte document. A document in Chinese or some other language with 1,000 characters is going to be bigger than 1 kilobyte. In Python, there's a special type called bytes that lets you like look at the actual underlying physical representation of your strings. Normally, we type out strings like this with single quotation marks. We haven't seen this R before, but you can put an R in front of a string to do what's called a raw string, and this ignores all these escape characters. So if I type normal strings like this, spelled correctly, normal strings, and print that, you'll see that \n actually gets displayed as a regular \n. But if I look at this raw strings right here with this R, raw strings like this, then you can see that what I typed in as \n up here is actually getting displayed as a \n down here. And if I print that, then it shows the actual \n value. So a raw string, whatever you type in is the exact contents of the string. You can't escape anything in a raw string. It ignores the escape characters. Normal strings and raw strings still are the same string type. So if I do this type function, normal strings like that, gives me this class string. If I do this type function on raw strings like that, also this class string. I can compare hello equals R hello like this, gives me true with these raw strings because they're the same type. This is just, sometimes we call it syntactic sugar to make putting in backslashes a little bit easier. Bytes are something totally different though. They look like strings. We use these quotation marks to create bytes, but they'll always be displayed with this B in front of the quotation marks. So this byte type, totally different than strings type. If I do type on example right here, you can see that it gives me this class bytes, which is different than the class string. And so if I did hello as a string equals B, hello like that, we'll get false because they're two different types. When you do an equal sign between two different types, even if like the semantic content of those types is the same, their equality is not the same, and so we'll get false right here. Every time we're working with strings on Python or inside of a file, or anytime wherever you have strings, they're always stored internally as these bytes. And there's something called an encoding, which converts between these bytes objects and these string objects. Bytes objects can only store 1 byte at a time. So it can only store ASCII values, can't store string values at all. Here we go. So the bytes type in Python, it's a container that stores multiple bytes, but each byte is just a single byte. So it cannot store non-ASCII values. If I try to, so we've seen before this exact quotation mark right here, no B in front of it like this. So that's a string, that's a valid thing. But if I put a B in front of it, it becomes a byte. That's invalid because all these things have code points that are bigger than the ASCII range, and so it can't store them. Next time in class, we'll go over converting between these bytes and these strings and loading up information from files. We'll see if the files again are stored as these bytes and how to do that conversion between those two types. I think this is a good stopping point for us for today. Happy to stick around and answer people questions about anything about this or about your project. But otherwise, see you all on Wednesday. Screen.